Okay. Yeah, sorry, it took me so long to start the meeting. I started the Zoom meeting at 11 o'clock and was just sitting around waiting for people to show up. Uh, and of course, I started the wrong meeting. You know, it's too much to keep track of nowadays. Okay. So, like I said in my email, this section, students sometimes have trouble with. It is kind of a, I don't know what to call it. I mean, it's just like anything in the class. It takes some getting used to. And in particular, so birthday problem. So this is like a framework, a conceptual framework. So part of the challenge is recognizing when a problem is one of those things. So the actual problem about birthdays is like, I mean, it's a cute problem, but it's not like anybody cares about birthdays in particular, but again, it gives you a nice little conceptual framework. Okay, so let me just start today by talking about chapter 3, which we're moving into. By the way, can everybody hear me and see the screen okay?
Yep.
Okay. It'd be sad to record this and then have those students not be able to see it. Okay, so just briefly, what's the purpose of chapter 3? To introduce foundational classic probability tools via classic examples. So the book takes like a layering approach. So for example, like chance trees, that's a classical play in the hits kind of tool, very useful, very necessary for a probability course. And we're going to investigate that using the game Craps. Today, we're going to talk about complementary probability, a topic we've already seen through the lens of coincidences and the birthday problem. But basically, this is what chapter 3 is. Every day, it's like there's a tool that the book wants to introduce to you, and it's like a classical tool of extreme use and importance, and they're going to do it through a famous problem. So coupon collector's problem is very famous, gambler's ruin, very famous, etc. So that's what chapter 3 is, and what we're going to do for the next 2 weeks or so, I guess. Okay, so now let's jump into the birthday problem and coincidences, again, as a way of thinking about complementary probability. That's a very useful tool. Okay, so let's set up the problem. Okay, so I don't know about you people. Back in the day, right, we used to go to things called gatherings, you know, parties, things like that, where human beings would like get in the same room together, sort of, I don't know, engage in socialization and such. You guys remember that sort of thing from the long ago. Anyway, so when you're at such a thing, you know, I'm usually trying to talk math, and you can imagine how that goes, right? So I don't know if people actually do this or not, right? But here's a question you could ask in a group of people, right? So you're just kind of like sitting around, like suppose like that person over there and that person over there, they have the same birthday. Like, oh, what a coincidence, you know? That's what this problem is basically about. So you're in a room of people. 2 people happen to share a birthday, and they're high fiving or whatever. Right? Like, oh, what a coincidence! What are the odds? You know, this section is about that, analyzing the probability of that. So again, that's just sort of a casual question. Who really cares, right? If you're in a room of 30 people and 2 people happen to share the same birthday, who cares about that? So again, like maybe you care, maybe you don't, but it gives a conceptual framework. So a lot of times you can have another problem you do care about, and you can recast it as that kind of birthday problem in a group of people, sort of thing. So anyway, so that's what this section's about. We're going to think about that question. Okay, so in particular this, how many people need to be in the room so there's a coin flips chance that you get a birthday hit like that? 2 people share the same birthday. And the birthday problem motivates a larger study of coincidences. Okay. So for this entire section, right, we assume 365 days in a year. Each day is as likely as any other to be somebody's birthday. In practice, that's almost true, but not exactly true. So all of you, I think, can guess what days might have more births than other days, right? You can maybe even guess a distribution. And I think it goes something like this. So here's February, the month we're in, right now. So birthdays kind of are like this, and then 9 months after February is a little spike. The actual distribution does something like that. But in practice, each day is almost as likely as any other to be somebody's birthday. Okay, so let's start with a warm-up question here. Let's do this one. How many people do you need to have in your room with you, right, to guarantee that you can find 2 people that have the same birthday? Or put another way, right, how many people do you need to gather together so the probability is 1? That you can find a birthday hit in the room, right? You can find 2 people that have the same birthday. How many people do you need to do that?
I mean, 365? I mean,
yeah. everybody agree with that?
Yeah.
If you have 364 people in your room, there's a very slight chance, but still a chance you wouldn't get a shared birthday, right? Because my birthday could be January 1st, then yours January 2nd, then January 3rd, January 4th, and so on, right?
Actually, well, 366.
Well, we're assuming, yeah, right. Sorry, yeah. 66, sorry. Right, so if you have 365, everybody's birthday could be different, right? Not likely, but could happen, right? So yeah, so you need like a lot of people, right? To guarantee that two people will have the same birthday. Okay, so here's a second warm-up question. How many people need to be in the room to guarantee that there is no shared birthday hit, right? So the opposite extreme. How many people now?
1.
Everybody agree with that? Because if you have two people in the room, they might share the same birthday, you know? So here's the range, right? The range of values we're thinking about. If only one person is in the room, there's a 0% chance you get a shared birthday hit. If 366 people are in the room, you're guaranteed two of them have the same birthday, right? So now, here's the real question, not a warm-up question. If there are n people at this gathering, what's the probability that two people share a birthday in the room? And then here's the actual real question, is the point of the section. How many people need to be in the room so that the probability of getting a birthday hit is a coin flip, right? 50%. Okay, so actually, yeah, just for fun, let's start with this real question too. Okay, so let me unhighlight this. Let's not think about that for a second. I just want to hear some guesses here. So we've seen the range of values, right? 1 is sort of the 0 probability, 366 is the probability 1. So now what if you want a probability of 50%? How many people do you think need to be in the room? You can just take a guess. I don't care if you know or not.
180.
Okay, so 180 is a very natural guess because it splits the difference between 1 and 366, right?
Although actually, it feels like it would be a little less.
Yeah, maybe a little less. So usually the first guess actually is like 183 or something, right? Because that's like literally right in the middle. So maybe a little less would be like 150, maybe. So sorry, go ahead.
That would sound too obvious. In questions
Yeah, right.
questions like this, the obvious answer is usually not the correct one.
Yeah, right. So if there are 180, as you say, this problem probably wouldn't be interesting, right? But I'm still curious to get you guys' guesses. So first we started with 180, then we backed off it. Somebody said less than 180, so I just put 150 down. Anybody else want to make a guess? I need some more numbers here. Somebody make a guess. Doesn't matter if you're right.
250.
250. Wow, going up like in The Price is Right, right?
90.
If you're on The Price is Right, you do 184 right now, right? Be a real jerk about it to outbid this person here. Any other guesses?
I'll go 90.
90, all right. Okay, so let me just look at this. Let's keep this collection of guesses off to the side for a second, and then come back and reevaluate them in a second. So again, 90. We're thinking about, do I need 90 people to have a coin flips chance of that coincidence happening, right? That person over there, that person there, like, hey, we got the same birthday. What are the odds, right? That's kind of thing. Okay, so now let's go back to real question number 1, and let's think about the probability that we get a birthday hit. Okay, now, the point of this section is to think more about complementary probability. Okay, so that's what we're going to do. So we're going to put the question on its head, or to the opposite. We're going to answer this question. What's the probability nobody shares a birthday? That's what we're going to answer right now. Right, that's the opposite, right? No birthday hits. So nobody gets the high five and be like, hey, we share the same birthday. So let's answer this question. Probability nobody shares a birthday. Once we get that, we can just take that out of 1 to get what we care about. So the actual thing we care about, right, it'd be like this, 1 minus that. So if we can do this probability, we can just take it out of 1 and we'll be done. Okay, so let's think about that. There are n people at the party. So let me erase this to make room for myself here. So we need a probability here that nobody shares a birthday. So we're going to do that just the classic way we did in chapter 2. We got to set up a fraction, right? So in the bottom is number of ways people have birthdays. And then up top, number of ways no hits. Right, that's sort of the schematic here, right? So in the bottom of the fraction, we have complete freedom how people have birthdays, right? Everybody can have the same birthday. I don't know, right? Nobody got the same birthday, anything in between, right? But then up top, we have to count what we care about. Nobody shares a birthday. So let me come up here. Okay, so let's think about the bottom first. So I have person 1, person 2, person 3, person 4, dot, 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 person n. So person 1, person 2, all the way up to person n. If we're doing the denominator here, number of ways people can have birthdays, how many options are there for person 1? How many possible birthdays do I have?
$365.
365.
Yeah, right. And then person 2, how many options there?
$364.
Again, right? You have complete freedom, 365, so on, dot, 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 365. So in the end, the multiplication rule says there are 365 to the n power ways of handing out those birthdays, right? So let me come back here and replace that and see if you have any issues with that. 365 to the n.
What's the numerator? Number of ways no hits?
Yeah, number of ways you get no birthday hits. So we're doing the opposite question. Like, what's the probability nobody shares a birthday? So up here, number of ways, should be a little bit more explicit about it. Nobody shares birthday. So speaking of the numerator, let's come back over here. Get rid of all this garbage work here. Okay, so again, I can think about distributing birthdays. I have person 1, person 2, person 3, dot, 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 person n. How many options are there for person 1's birthday?
365.
Okay, good. How many options for person 2?
364.
Yeah, it can't match, right? So person 1's birthday is out. How many options for person 3?
363.
And so on, right? Okay, now let's make sure I don't mess this up. I think this is at the end here, 365 minus n plus 1. Is that right? What's the pattern here?
Yeah, that's right.
Okay, yeah. So now you're going to multiply those down the line, right? So up top, I have here 365 times 364 times dot, 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 times 365 minus n plus 1, like that. So we have our answer basically, right? Right now we just do 1 minus that. Now I'm going to go to the computer here and start typing this in a second, but notice this kind of thing up top can be kind of obnoxious to type in depending on what n is. If n is, say, 30, you really want to type 365, 364, 363, you don't want to type that, right? So let me just point out this product here, this 365 times 364 times dot, 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 365 minus n plus 1. That is the same thing as 365 factorial. So 365 all the way down the line, right? All the way down to 1. But then you got to divide by enough stuff that you kill. So let's see, 365 minus n factorial, like that. So 365 factorial starts at 365 and goes all the way down to 1. You don't want to do that though, right? You want to stop, you want to stop right here. So 365 minus n, you want that out of there. So you got to cancel it. 365 minus n minus 1, got to cancel that. Minus n minus 2, and so on, right? So let me just pause here and ask. Any questions on that formula there?
If there were like 10 people, it would be 365 factorial divided by 365 minus 10 factorial.
Yeah.
Okay.
Right. Because then with 10 people, it'd be 365, 364, 363, 360. You got to do that 10 times, but then you don't want to go any farther than what, 355, I guess, be the last one. You don't want to go any farther than that. So you want to make sure you cancel all the extras off, you know, because that 365 factorial just keeps going. You want to make sure it doesn't keep going.
Gotcha. And that would just be the numerator?
Yeah, so now we have just like this nice little closed form for the numerator when it comes time to type things in. So 365 factorial divided by 365 minus n factorial, like that. Okay, so now let's go to Wolfram. And again, I can't stand typing on this iPad, so I'm going to quit typing here. Go to my computer. Oh, and Jacob, you're here today.
Yeah, we leave tomorrow.
Oh, okay. Whoop, not that. Where is, okay. And so I'm always blaming Apple TV for slowing my computer down. I guess it's Zoom. Okay, so let's start typing in some numbers here. So let's say there are 3 people at the party. So that'd be 365 factorial divided by 365 minus n factorial. I'm going to be real careful with my parentheses here. Divided by 365 to the third. Oops,
Zero,
not
right?
n. I don't want n. So n equals 3, right? There are 3 people there. Here's the probability that 2 of them share the same birthday. This should probably be pretty low, right? Because for 3 people in the room, right? I don't know. It seems pretty unlikely that 2 of them would share a birthday. That is pretty unlikely, right? 0.8%, not particularly big. So that makes sense, right? Now I'm going to start typing some of you guys' guesses in here. So the smallest guess I received was 90. So I'm going to put 90 there, 90 there. So here's the probability that in a group of 90 people, 2 people share a birthday. Okay, so here's the answer, 0.99999.
Let's go.
Sounds like 100%, right? Basically. So if there are 90 people in the room, you're basically guaranteed 2 people will share a birthday, right? So I don't know, it seems like this big coincidence maybe, but if you have 90 people, I don't know. This is saying, right, 2 people will share a birthday with basic certainty. So maybe 90 is actually too big. And so, by the way, if you type in 180 here, which is the first guess, of course, the number just gets even bigger than 0.99999 because now you got more people. With 180 people in the room, right? See that? What is that, like 39s or something? You got 180 people in a group. It's certain that 2 people share a birthday. Okay, so 90. Let me back off. Let's say maybe there are like, I don't know, 60 people in the room. It's still 99.4%. So if you have 60 people in your room, right, at a party, it's basically guaranteed that somebody shares a birthday with somebody else. Okay, so the overall question was, when do I get a coin flip chance? So let me just show you. Let's say there are 23 at your party. I just chose that at random. Let's see, 23 people at your party. 0.50. Okay, so to have a coin flips chance that 2 people share a birthday at your party, you only need 23 people, which is much smaller than all the guesses, right? That's why this question exists, because...
What's 22?
Huh?
What's 22?
22 will be slightly under 50. Might be like 49 and a half or something. Maybe 48.
Yeah, I doubt you chose that number at random.
Yeah, I was lying. Sorry.
Yeah, you're talking about coincidences, but the probability of that being a coincidence is too low.
Yeah, so when I'm pulling the strings, right, there are no coincidences. But even 22 people, right, basically gives you a coin flip chance. I mean, it's 48% or so. So all that to say, this question exists because it's counterintuitive, right? Like, if you just take a guess, you're not going to guess the right answer. Everybody guesses too big, right? Nobody thinks that 23 people is enough to get this coin flip chance of this coincidence, but it is. And the reason is because if you think about what it takes to get a birthday hit, right? If there are 23 people at your party, here's the number of ways you can sort of like pair people up and see if they have a birthday hit or not, right? So from the 23 people here, if you want to count the number of ways to pair them off, and then every pair asks, hey, what's your birthday? There are 253 ways. Is that it? Yeah, well, anyway, so there's 253 ways of pairing people up, right? So there's lots of pairings you can get from 23 people. And the pairings are what matter, right? Because you pair up, you ask if you have a birthday or not. So that's why the probability is so high, because there's so many pairings you can do. And also, let me show you this before I hop back on my iPad. This picture here, the blue line is 50%, the red line is 100%. This black curve is that it's that formula in terms of n. What was it? 365 factorial divided by 365 minus n factorial over 365 to the n, 1 minus that. That's what this black curve is. It's filled in the gaps in between the integers. But anyway, you can see it starts at 0, because if there's 0 people, the probability is 0, you get a hit. And then when there's 1 person, probably a 0. When there's 2 people, it jumps up just a little bit, but still tiny, 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 right? But anyway, here's 23 people. Here's 23 people, and that's where it crosses the 50% line. And then by the time you get to, I don't know, 50 people, 55 people, it's basically a guarantee that 2 people share a birthday. Once you hit, what, 65 people, the black curve and the red curve are identical, you know. So really, based on this graphical evidence, you really only need like 60 people at your party to have a certainty, basically, right? Almost a certainty that 2 people share a birthday. Okay, that's the birthday problem. That's a fun sort of like classic problem. And again, there are 2 points here. The first point is that complementary probability gave us that probability without a whole lot of struggle, actually, right? Let me start my iPad again. If you didn't use complementary probability, this would be a very difficult problem to do, because what would you have to do to answer this question? Your numerator would be counting the number of ways that at least 2 people share a birthday. That seems real hard to do, if you ask me. You know, but then if you flip the question on its head and you're like, nobody shares a birthday, it's not so bad. So that's lesson 1, complementary probability. Lesson 2 is that things can be counterintuitive, right?
Daddy.
What's up, bud? Buddy, I'm in class right now, okay?
Well, I want to listen to something on the Kindle.
Sorry, just a second.
Said I couldn't.
Tell her that you can't. Okay. Sorry, so everything just falls apart societally nowadays. So my wife had to take my baby to a doctor's appointment, and then my 2 older kids are just fighting over who gets what upstairs. Anyway, what was I saying? Oh yeah, so it's a counterintuitive problem. Also though, this problem, as we will see, provides a general framework for solving problems involving complementary probability. If you can just take your problem you're doing right now and frame it as a birthday problem, you can get a lot of mileage out of it. Okay, so here's the big punchline of this section. If there are n people in a room, each day of the year is just as like as any other, blah, blah. The probability at least 2 people have the same birthday. Now, this is not obvious at all here, but I'm just going to assert it to you as a theorem. The probability of n is 1 minus this exponential. So what I'm claiming here is that this 1 minus exponential thing, I'm claiming that's basically this. I'm claiming those are approximately the same thing. And as n gets bigger, actually, the approximation gets better and better. So when n equals 2 or something, it's not a great approximation, it's okay. But for n equals 23, it's pretty good. Okay, so then more generally, you know, 365, there's nothing special about 365. If there were k days in the year and still n people, then here's the probability of a birthday share. So really, a lot of the homework, you might read a problem and think, wow, that seems pretty hard. How am I supposed to do that? And the answer is, if you can just recast it as a birthday problem, there's this formula right here that you can just grab. So speaking of that, let me show you a couple of birthday problems in disguise. Get rid of all this highlighting. Okay, so here's a question from the very first day of class. And now that I'm looking at it, I think this 100 was actually a 400 or something, but it doesn't matter. That number is arbitrary. Okay, so a lottery official has some leftover money. They're going to purchase 100 cars and raffle them off among the 1 million subscribers to the lottery. So the way this works is each subscriber is given a unique number between 1 and 1 million, and then a computer just chooses, it does this 100 times, chooses a number between 1 and 1 million at random, but the computer does not is not careful about double carring or something, right? So it maybe chooses 50 this time and then chooses 50 on round 8 or something, whatever. So the question now is, what's the probability someone wins one or more car? So this, of course, has nothing to do with birthdays on its face, right? So the question is, what is this question doing here, and how would you use the birthday problem to solve it, right? So let me just walk you through that, and then you guys will try a couple on your own. But notice, in any birthday problem, you have to be able to tell this story. N people in a room, K days in the year. So there has to be something playing the role of the people in the room, and there have to be something playing the role of the birthdays, right? And so notice in the original birthday problem, we were thinking of it as like person 1, person 2, person 3, you know, and so on, right? And each one of these people gets assigned a birthday. So this person maybe gets assigned 365, that's December 31st, right? This person gets assigned to 3, that's January 3rd. This person gets assigned to 32, that's maybe February 1st, and so on, right? So each person in the room gets assigned a number, and the number happens to stand for a birthday, but doesn't have to. Okay, so let's think about that framework here. Here I have 100 cars. So here's car 1, car 2, car 3, car 4. And notice each car is assigned a number, right? Does everybody agree with that? What are the possible numbers you could assign to car 1?
1 million.
Between 1 and a million, right? Each car is assigned a number between 1 and a million. And then car 2, car 2 could be assigned to the same number as car 1, maybe, right? That'd be like sharing a birthday, right? So it's the same problem. So here, we can make a little schematic like this. We can say cars are like the people, and then number between 1 and a million, that's like being given a birthday number. And as soon as you make that identification, it's like, oh, okay, well, now I got this formula, I just got to use it. Okay, so again, this problem, you could have rediscovered this, and that's what students do a lot in the homework, right? So a lot of times, no matter what I say, students won't use this formula down here. I can say, hey, you should use that because it makes it easier, and then students will still do this thing up here, which is fine. You could write down something analogous to that in this question, but why rediscover the wheel, right? We already did that. So here we say, okay, there are 100 cars, so that's like having 100 people. And instead of 365 birthdays, there are 1 million birthdays. Like that. And once you make that identification, you just hop right up to this and plug in N where it goes and K where it goes. So I'm not going to hop onto my computer to show you that, but we can all calculate that maybe, right? We just go to Wolfram. Does anybody have it? Got to be a little careful with our parentheses, right? So it's e to the power negative 0.5 times, in this case, 100 times 99. That has to be divided by 1 million. So for me, Wolfram gives me this 4.94%. Why am I using this rainbow pencil? 4.94%. Okay, so again, the challenge of this question is like recognizing it as a birthday problem. And once you recognize that, you just use that formula and you're done. Sorry, does somebody have a question?
Yeah, so is that the probability someone wins one or more car, or the probability that they win more than one car?
Yeah, right. So that's a good point, Calvin. So you'll notice I ripped this straight from the slides, right? And the slides had the same issue, so I should have remembered that. This question here, as asked, right, as literally written, what's the probability?
Well, isn't it 100? Like someone will win a car?
Yeah, it's a dumb question, right? Somebody's going to win a car, right? So the actual, so 100%. So we talked about this whatever day that was, right? I was like, oh, that's a typo. I should fix that. And I fixed on the slides, but then didn't fix it here, right? 2 or more cars, right? What I should say. And I'm so used to asking the real question and not the dumb one that I did ask that I didn't even notice it says 1. Right? Does everybody say that Calvin's are right? You know, that the question I asked was actually silly. Other questions on that one? Like, do you guys see how it's a birthday problem? You see how that framework is useful? Okay,
Yeah.
so I want. Oh, go ahead. Sorry.
No, I was just responding to your question. Sorry.
Oh, you're saying you're okay? Okay, so let's. I have one more example to show you where there's a birthday problem embedded, but again, some things are not birthday problems, but the idea of the section is, can you use complementary probability to save you some work? You know, so here we use complementary probability to get us this formula here, and it was all right. So this next problem, I'm just going to show you that you can, sometimes there's a birthday problem there, sometimes there's not, but regardless, sometimes complementary probability is still very useful. So we'll do this example for maybe 5-10 minutes, and then I want you guys to try some homework before we go, just to make sure you can do it. Okay, so let's start with this. So the Bulgarian 642 lotto. So it's just a standard lottery. There's nothing special about it. There's no Powerball number at the end, but you choose 6 different numbers between 1 and 42, right? That's what the 6 and the 42 are telling you. 6 numbers between 1 and 42. Order doesn't make a difference. And of course, you're trying to guess the number that comes out, right? Okay, so here's the first question. The lottery runs 3,000 times. What's the probability the same outcome occurs at least twice? Okay, so what does that mean? Like,
Daddy,
sorry, just one second.
can I have the iPod?
Yes, go ahead. Okay, so yeah. So maybe like today, the outcome is 1, 2, 3, 4, 5, 6, and then maybe 200 runs from now, it's still 1, 2, 3, 4, 5, 6. What's the probability that something like that happens? Is the question. Okay, we'll just put it somewhere else, please. Thank you. Okay, so now the question is this a birthday problem? Because if it is, then what you need to do is do this kind of translation, right? And if you can do that translation, then you're basically done, because you hop up to this formula here. So let me just put that to you guys. Is there any way to cast this as a birthday problem? I guess the heart of the birthday problem is just drawing one of these little schematics, right? So if you do that, what would one of these little slots represent?
1 through 42.
I'm sorry, say again.
A number between 1 and 42.
So you have to think about each of these being an individual outcome or something, right? So a number between 1 and 42 is not like a lotto outcome, right? I mean, it's part of what you do, what you choose to play, right? But
So
it-
6 numbers, each between 1 and 42 then?
so you're saying for this, oh, I see what you're saying, right? You're saying this is like a run of the lotto, basically. That's what you're saying?
Yeah.
Yeah, right. That slot represents like you played the lotto and there was an outcome, right? Okay, so let's go with that. So if that's the case, you're going to do that how many times? 3,000 times? Okay, so let's see if this framework works. So what Jacob is saying is that maybe each individual lotto run is playing the role of the people, right? Because before with the birthday problem, each little slot represented a person. So if that's the case, what comes up here? Like what kind of things would you fill in up there? So in other words, for that first run of the lotto, right? what kind of number could you assign to that?
$42.
You have the right idea, but each individual run, it's not like there are 42 options for it or something, right? It's not there are 42 outcomes. Now you're right. If you just chose one number between 1 and 42, you'd be right. You'd put like a 42 up there, right? There's 42 ways for that first lotto to run. But because you actually choose 6 numbers, there's a lot more than 42 ways for that run to shake out.
42 choose 6.
Yeah.
Let's. Hang on.
Sorry, what'd you say after that?
Oh, I was celebrating, saying "Let's go."
Oh, okay. Sorry. For some reason on Zoom, sometimes I can't hear very well. I blame Zoom and not like my ears. Yeah, so each individual run has the same number of like options, right? 42 choose 6. Just like for each human being, right, has an option between 1 and 365 for their birthdays. So as soon as you make that observation, you're like, okay, let me get rid of this. So now what's playing the role of the people is each lotto run. And what's playing the role of the birthdays, the 42 choose 6 possible lotto outcomes. So like, okay, I got like slots, right? And each slot has so many outcomes. In this case, it's not between 1 and 365, it's between 1 and something way bigger. So 42 choose 6 is way bigger, right? Let's see what that is. It's like 5.2 million or so, you know, a lot of ways you can play that lotto. But once you make that observation, each lotto run, there's 3,000 of them. 42 choose 6 of those. Now you hop back up to this formula here and just plug those in, right? You just come in and plug in. N is the number of people, K is the number of birthdays. So does anybody have that, or should I type it in? All right, I can ask Wolfram. So let's see. So now I have my old formula up with 100 and a million or whatever, right? So now I have 3,000 people, and then 42 choose 6. And Wolfram gives me roughly 58%. So better than coin flip, right? So if you're going to let a lottery run for a long time, even if there's a ton of outcomes, the probability you see the same thing twice sometime, right? Like, oh, the thing I saw today, I saw it 2 months ago. The probability of that kind of thing happening is not particularly unlikely. I mean, the longer the lotto runs, the more likely it gets. So again, the challenge of the section and why students generally find this homework difficult is this kind of thing, right? You have to recognize that what you're looking at is a birthday problem, or I guess you don't have to. You can rediscover this logic every single time, right? You do that if you want to, but I don't know. It makes things, I don't know. We don't want to reinvent the wheel every time. But this exact same logic will work for that one we just did. You're just rediscovering what we had. So speaking of that same logic, this number 2 now, this is not a birthday problem, but you can still use the same logic, still a complementary probability thing. So let's think about this. Okay, so in 2009, this lotto actually chose the same set of numbers 2 days in a row. That seems pretty unlikely, right? I don't know. So let's just ask, just in a vacuum, right? What's the probability choosing the same set of numbers 2 days in a row? Okay, so this now, sorry, this is not complementary probability. We're going to use this. We're going to use this number 2 to do number 3. And then I'm not sure if we'll have time to do number 4, because I do want you guys to try a couple of homework questions. Anyway, so for number 2, up here we have to count number of ways to get the same twice in a row. And then beneath, just number of ways in general, whatever. Complete freedom on the two drawings. Okay, so let's count that over here. Let's do the denominator first. There's today and then there's tomorrow, right? How many options are there for this lotto on the first day?
42, choose 6.
Yeah. And if you're in the denominator, how many options for the second day?
$42, choose 6 again.
Yeah,
Right.
complete freedom. Yeah. So it's 42 choose 6 squared, which is real big, right? Because 42 choose 6 was whatever it was, 2.5 million or something. So 42 choose 6 squared. Okay, now let's think about up top. Up top, you're supposed to get the same thing 2 days in a row. So how many options for the first day?
$42, choose 6.
Yeah, complete freedom on the first day, but then how many options for the second day?
1.
Just 1, right? So now we come back over here, slot in 42 choose 6. Okay, so let's ask computer what that is. It's going to be small, as you can imagine, right? So that's just 1 over 42 choose 6. Oh, Wolfram's really thinking about that. It's 1.9 times 10 to the negative 7, right? It's like really small. Right? From our perspective, it may as well be 0, I guess, right? So again, this is like in a vacuum, right? Like we just had a drawing today, right? What's the probability tomorrow matches? Really small, right? Okay, so now let's finish up with question 3, and maybe I'll leave question 4 for another time, just for the sake of time here. Okay, so now, let's ask a broader question, right? So let's say this lottery's been running for a long time, right? Twice a week for 32 years, let's say. You know, maybe it's been doing it longer. Maybe it runs every day. I don't know. These are just arbitrary choices here I made. Okay, so now let's ask a much broader question. It's running for a long time. What's the probability that sometime it drew 2 numbers in a row, right? So not like today and tomorrow, but just over the span of 32 years, what's the probability it draws the same number twice in a row? Let's think about that. And again, for the sake of time, I'm just going to show you the complementary logic here. This isn't really a birthday problem in any meaningful sense because there's nothing to be the birthdays and the people. You can think about why that would be. But anyway, so here, though, you can still get at it complementarily, if you would like. I think about it like this. So twice a week for 32 years. So here's first run, second run, third run, fourth run, fifth run, sixth run, seventh run, eighth run, ninth run, right? So on, right? Twice a week for 32 years. How many runs is that? 2 times 52 times 32, is that right? So there's first run, second run, run 3328, right? So more than 3,000 runs of the lottery. Okay, so let's again set up a fraction. In the bottom of the fraction, we have complete freedom about how these runs go. And in the top, we have to think about our restriction, right? So in the bottom, it's the same lottery, right? So we have complete freedom every single time the thing runs. So 42 choose 6 raised to the 3328 power. That's the really gigantic, you know. Now we're lucky nowadays we have Wolfram. Because Wolfram, I mean, if you hand that to Wolfram, it's just going to tell you that's huge. Like it's not even going to try to tell you what it is. But it can handle it inside of fraction. So like when you ask Wolfram to divide something by that, Wolfram can handle it. That's nice. Okay, so now let's flip the problem on its head, right? Let's think about never. So never twice in a row. That's the opposite. Let's count that, right? If you're never going to get twice in a row, let's think about that. So if you're never going to get twice in a row, how many options are there for the first lottery? So we want to avoid twice in a row, right? But that assumes that we've had at least 2, right? So how much freedom do you have on this first run?
You have complete freedom on the first run.
Yeah. So whatever can happen on the first run, right? Now, though, on the second run, we can't get 2 in a row, right? So how many options do we have? Sorry, did I do this? Yeah, that's right. How many options are there for the second run?
Uh, 42, choose 6, minus 1.
Yeah. So you just can't match the first one like that. Right, but you can be anything else, just can't get 2 in a row. What about for the third run? How many options do you have there?
Forty-two, choose 6, minus 2.
You're close. You just can't get 2 in a row, right? But you could match the first one.
Gotcha.
Everybody see that? Just no 2 in a row. So then dot, 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 right? All the way down the line. It's 42, choose 6, minus 1. So back over here, we have 42, choose 6. And then we have 42, choose 6, minus 1. And that's all the other runs. So that's not what we want. So now, 1 minus that. I take that out of 1. Let's see what that is. So again, Wolfram is like a miracle worker that can handle these gigantic numbers. So you got to be careful with your parentheses, but you can just type all that in. Choose 6 minus 1. That gets raised to the 3327, and that's divided by oops. So if somebody has it, you can shout it out. 3327. I got to divide it by 42, choose 6, raised to the 3328. Okay, so Wolfram gives me 0.000634. Okay, still small, obviously, but not nearly as small as this. It's increased by an order of magnitude of like 100, right? Like it's gotten, relatively speaking, it's gotten way bigger. So, if you zoom out, right? If you say, what's the probability this crazy thing happens like today and tomorrow? The probability is basically 0. But if you say, well, what's the probability it happens sometime? This is still small, obviously, but it's not 0. And of course, if you let this lottery run, I said twice a week for 32 years. What if it runs daily for 50 years? Then these numbers up top just keep getting bigger and bigger, and this corresponding probability will just keep getting bigger and bigger. That number will actually limit to 1. If you let this lottery run for millions of years, you'll eventually see 2 in a row. So this last question I'm not going to do for the sake of time, but it's basically just that. Like, instead of doing whatever it is, 3,328 runs, now you just have way more runs because you got lots more lotteries running. It's the same idea. Okay, so again, this one here, this number 3, it's not a birthday problem, but you set up the same kind of fraction and you get it from thinking about the complement and then taking out of 1. So again, I apologize. On Zoom, I don't know why. Things take longer. Seems like things should be shorter, but are there any questions on any of these examples with this lottery? So before we do some homework, just for 10 minutes, so I should point out, once you plug this into Wolfram, it is fun to monkey with these numbers here. So you can ask, like, how many runs of the lottery do I need to get a probability to be up to 50% or 80% or whatever, right? And it's probably going to take millions of runs. But again, in the long run, right, you'll eventually see something unlikely. Okay, so now let's hop to the textbook. I think I'll stop recording.